Hi, I'm Nancy Huntley, and I'm here to welcome you to Science Unwrapped. Thanks for coming out tonight, and I want to thank the College of Science who sponsors Science Unwrapped. This evening we're continuing our series on powers of 10, from the super largest things that we can only kind of imagine, but we can talk about mathematically, to the teeniest, weeniest ones. And so we're moving along to the scale of whole planets, like our planet. So we'll be in this room for about an hour. We'll be done in here about 8. For most of that time, our speaker this evening will give a presentation, and she may ask you some questions as she goes. But when she finishes talking, please stay in your seats for a few more minutes so there's time for questions and answers. And please, listen quietly during that time as well, so that people who want to hear the answers to the questions can hear them. And then at 8 o'clock, we'll send you out of the room to go see all the cool, fun things out in the halls. And so please hang around there and go see some of the scientists we have in the halls and learn the things they have to show you. So our speaker tonight is Dr. Carol Dehler from the Department of Geology. She has 3 degrees in geology. Her undergraduate degree is in geology from Humboldt State University in California, and then she has a master's degree in geology from Northern Arizona University and a PhD in Earth and Planetary Sciences from the University of New Mexico. So she knows a lot of geology, and her specialty is deep time geology, the oldest early history of the Earth that we can understand from studying geology. So she studied super cool stuff like the Snowball Earth hypothesis, that our Earth was once basically an ice ball, and also evidence of the origin and timing of the first microbial life on the Earth that's preserved in rocks. So she will talk to you tonight about science at the planetary scale and what we know about our planet. Thank you.
Thank you very much. Welcome, everybody. Thank you very much for coming, the last Science Unwrapped of the season. So I was invited to be in this Powers of 10 themed Science Unwrapped series, and that's very appropriate for someone like a geologist, because we think in powers of 10 all the time. And we think of time in powers of 10. So we think on very small time scales, medium time scales, and very long time scales, such as 10 to the 9th billions of years. Okay? And even though I'm under the planetary category, I'm an Earth scientist. I don't tend to study other planets, but some geologists do go off and study other planets, and I'll show you a picture of that in a second. Let me get used to this clicker. Okay, so what is earth science? And earth science is the same thing as geology, and it's the same thing as geoscience. It has a couple of different names. And earth science, we look at the earth, it's the study of the earth, but we look at the earth in kind of 4 overlapping spheres, right? So there's let me use the pointer here. There's the biosphere. What does bio mean? Life. Yes, and there's the hydrosphere, hydro meaning water, and that's the lithosphere, lithos meaning volcanoes, lava, it's more fundamentally just rocks. Yeah, like the crust. Oh, good, yes. Okay, and then we have our atmosphere here. And so we're very interested in how all of these spheres interact with one another and cause one another to change based on other ones happening. But we look back in Earth time. We are Earth historians, and so we want to know about things like the Paleobiosphere, and an example of that would be looking at a piece of petrified wood, okay? We want to learn about the Paleohydrosphere. What are these things? Does anybody know? They're not fossils. What are they? Waves. They're ripples. Yeah, these are called ripple marks, and these are, oops, got to get used to that. These are made by waves, so we know that water had to be present when this sediment was actually laid down, okay? So Paleo Lithosphere is any rock you want. Do you recognize this one? It looks like obsidian, right? So that's a volcanic rock. So all you have to do is pick up that rock and say, hey, a volcano erupted, and a certain kind of volcano erupted. So that gives us information about the past. And the atmosphere, we can study things like ice cores that trap gases that were present in the atmosphere in the past, okay? So that's what earth science is. Now, what is an earth science? What do we actually do? What do earth scientists do? Well, I think this is the typical idea that most people have of what a geologist is, somebody in a plaid shirt with a flumpy hat on, stumbling around in mountains. And you're right, or that's what we like to do the most. And here's some students here, and they are what we call being in the field, and they've got their notebooks, and they're being very good, and they're using hard lead, and they're being neat, and they are drawing this geologic feature. Let's see what happens if I do this. Yeah, and so what they're drawing here are these layers here that are actually tilted, the strata, and they're also looking at this unusual feature here that folds down and wraps down around. And so they're drawing this feature and studying the physical properties of the landscape, okay? But we do other things too. We love to model natural systems and understand natural systems of the past, and do they operate in the same way? This is an example of Dr. Pedersen had built this really neat big sandbox that we play in a lot, and during Rock and Fossil Day, some of our graduate and undergraduate students showed people how to model streams, and they added sand, and they added water, and they added slope, and things like that. Over on the right here, these gals, this is undergraduate Michaela, and that's a graduate student, and she's in the audience probably, Heather. They are doing geochemistry. And so in geochemistry, you're studying the mineral and elemental properties of a rock that maybe you can't see with the naked eye, okay? And that can tell us a lot of things about a rock's history and what was going on in that period of Earth history. A quick, short lesson, rock. So what's a rock? Rock is granite. Hey, you cheated. Okay, so granite is a kind of rock, and rocks are made up of minerals. Very good. And granite is made up of feldspar, quartz, and biotite, for example. But then what are minerals made of? Molecules. I'll take that. Elements. Okay. Elephants. Elephants is fine too. So, for example, quartz, the mineral quartz, is in the rock granite, but it's made up of silicon and oxygen, the elements, okay? Oh, and here comes Lapis Lama, and he says, make sure to stick around for the activities after the talk, because we can look at rocks and minerals and look under the microscope and stuff like that. All right, other things earth scientists do are to go on and be astronauts like Jessica Watkins here, or potentially an atmospheric scientist like Margarita Maranova. So you can do big things with a geology degree or 2 or 3 or 4. So we think in time, we think in pretty big time scales. I said we were Earth historians, but yeah, we don't think about time in days or seconds or hours. We typically think in years, and more often tens of years, thousands of years, millions of years, and billions of years. That's where the powers of 10 come in. And I personally like going back into deep time, which is 10 to the 7th, 8th, and 9th. So using powers of 10, this is for the kids in the audience. If 10 to the 1 is 10 years, what's 10 to the 2? 100, okay. 10 to the 3, 10 to the 4. Okay, we're right so far. 10 to the 5. 6. 7, 8. So 10 to the 8th is 100 million years, okay? And then there's 10 to the 9th. which is 1 billion years, which is really, really makes me happy. So who can tell me what the age of the Earth is? Raise your hand. What's the age of the Earth?
3.4 billion.
I hear 3.4 billion. Anyone want to go higher than that? 0.6? 4.6. Who said 4.6? Oh, could you come up here for me? That's what you get for being. That's what you get for being right. All right. Come on over here. What's your name?
Will.
Will. Thank you, Will, for being my model. I need your arm, and I need your, what arm is this? This is your left one, so you want to hold that out, okay? And one kind of classic way to think about geologic time and how insignificant, what an insignificant amount of time we've spent on the planet is start with the shoulder. The top of the shoulder is when Earth begins, and the very, very tippy tip of the middle finger is today. Okay, so we're in today. We're at the tip of the finger. And these, keep it up. Okay. And then we have, thinking in powers of 10, we have 1, 2, 3, and 4 billion, and back to 4.6 billion. So this is our timeline. It's sort of a distance as well, right? But that's our timeline. But not everything happens on the scale of billions of years. We have some pretty interesting things that happen. They come in right about here. And that's where we start seeing skeletal remains in the fossil record. That's where we see evidence of animals that were making hard parts, making shells, et cetera. Okay, so that's there. That's 542 million, okay? Something else you might be familiar with is what? Dinosaurs went extinct at about 66 million years ago, and that brings us up to about there in geologic time, okay? And I'm running out of room here, so and that little red line is going to show up here, and I'm going to tell you what's going on in this last little very tippy tip of your fingernail. So this very, very tippy tip is about 3 million years worth of time. And we had our last ice age came in about there. And the end of our last ice age was at about 12,000 years, so that was at about there. Okay, hold on, am I hurting you? No. Okay, good. The beginning, when Homo sapiens appeared in the fossil record, was a little bit back farther, about 300,000 years ago. And then ice cream came in at about 1960, which I believe he bit off earlier today. All right, so thank you very much for your participation. Okay, so what I want to do is give you 4 little vignettes showing examples of different amounts of geologic time on geologic time scales. So I'm going to show you a 1,000-year type of a geologic problem, and then how we would date that geologic problem. And then I'm going to go back in time and back into billions of years. And so what I've made for you is another sort of time scale, and I apologize. But here's Earth being born. Actually, I should get you back up here again, but it's okay, because I don't think your arm will go that way. So here's the Earth, and it was a long and circuitous route through geologic time, through the billions of years. We get back here to this very profound boundary in the geologic timescale in the geologic record, and that's when animals first appear, their hard parts first appear, which is at the base of what we call the Cambrian, and I bet a lot of you are familiar with that. And a lot of the organisms that show up in Cambrian time are trilobites that I bet a lot of you are familiar with. But then today is here again at this green point. And so I'd like to show you these vignettes. I'm going to talk about a short-term vignette that tells us about climate change. I'm going to take you back a little farther in time, and we're going to talk about dating faults and how fast a fault might move with a different kind of technique. Then we'll go to the Snowball Earth glaciations, and we can think about Snowball Earth glaciations. And then I'm going to take you way back here and show you the oldest mineral that's been found on the planet, and that's the oldest evidence of the age of the Earth that's from Earth. Okay? So let's go on. Oh, so this is the big word. This is the powers of 10 word. This geochronology is the study of the age of rocks. So a geochronologist dates rocks, and then we figure out what that date means. And geo means what? Earth. And what does chronos mean? Time. So you can see where that word might have come from. All right, so let's start here. Let's start here with our 10 to 1,000 year time scale example, and we're looking for a climate record in here. And so what this is called, do you know what this is called, anybody? That's a tree. Oh, yeah, that's a bristlecone pine. You're absolutely right. And these can be, the oldest one is close to 5,000 years old. So we like to use older trees to study tree rings because they have a longer record of climate housed within them. So if you cut down a tree, then it's not going to grow another growth ring. But you can see these individual growth rings, and the tan is the wetter part of a year, and then the brown is the drier part or getting into the winter season. And so each of these is an annual lamination, okay? So you can count all of these up and figure out the age of the tree. And I can't think of, Tammy, what's Eric's last name? Eric Allen. Oh, so Eric Allen was one of Tammy's graduate students a few years ago, and part of his thesis was coming up with a climate record for the Bear River range in our area. And he, instead of cutting down the tree, is using what's called a tree core, and it's a very, very narrow tube. You wind it into the tree, and you pull out this sweet little tube of wood that then you can see all the rings within that, and it's not harmful to the tree. And he's even drilling into dead wood because you can get a continuous record if you look at living trees and then trees that have just died. You can get a longer record. But whether you cut them or you core them, what's interesting is sometimes the growth rings are fatter, and they might be fatter for a significant distance, and then sometimes they're closer together. Let's see, like that one's pretty close. These three are pretty close together. And I like this example over here. See how close together these guys are? And then these guys are pretty wide, and whoa, look at those growth rings right there. So those are telling us that it was really wet during these times, not quite as wet here, and it got pretty dry here. So this is a paleoclimate record, if you will, by looking at tree rings. So if you lay one of these cores out and you know the age of the tree, you can then line up those, you can line up those tree rings with the dates and get a climate record based on how fat your tree ring is, okay? So when it's really low right here, what does that mean? It was pretty dry, right? And then, oh, that was pretty good, pretty good. Oh, yeah, it was really wet here, and then going down again in the 2000s. And so these are very important tools for understanding regional climate change. All right, so now we're going to go back a little bit farther in time, and we're going to look at some faults and think about fault movement and how fast faults move. Do you recognize the Moab Valley? Moab Spanish Valley? Many of you have been there? Yeah? Okay, check. So here's some tall cliffs on this side, tall cliffs on this side. We're looking north here, and then there's this sinking valley. This valley is sinking, and here's the Colorado River. So there's faults on either side of the valley, okay? And there's a drainage coming into the valley on the side, on the east side, called Mill Creek. And it crosses those faults, that fault zone. Okay, so and the Mill Creek has been there for a while, and it's left river deposits up here in the high parts on this part of the fault. And it's also left river deposits down here below in the lower areas. And so a good way to date river sediment, maybe to figure out how these faults are moving through time, is to sample, USU. What did I do? Should I hit OK? Or should I hit the X?
This is still a presentation mode.
Hold on, hold steady, steady. Easy. Wow. You guys would have let me talk for a while there before I changed that slide. Da 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 da. Sorry about this. Okay, where were we? Dun, 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 dun. Oh, Moab. We were in Moab. Nice Moab. Okay, so we talked about tree rings. Here we are in Moab, and this valley is sinking. And we talked about being able to sample these different river deposits that are on either side of these faults to get a feeling for maybe how fast the valley is sinking. Okay? And here's where I was, is one of the best ways to date relatively young, like tens of thousands, hundreds of thousands of year unlithified river sediments is using what's called luminescence dating. That there's no way that I can explain how luminescence dating works, especially with Tammy in the audience. But I got this right from Tammy. It provides an estimate for the last time the sediment was exposed to light or heat. And so once that river deposits that sediment, when that sediment gets buried, if it doesn't see light again, you can sample it deep down, make sure not to let any light hit it, and bring it back to a dark lab, and it will luminesce when you do crazy things. You prod it and with different lasers and lights and things, and you get an age, okay? And so Tammy's putting in a long tube here, so she's getting back away from the outside of the outcrop, so she's going to get some sediment that hasn't been exposed to light. And then over here on the right, it looks kind of weird, but this guy is holding a black tarp over the person that's actually sampling a sample so that it doesn't get exposed to the sunlight, or that will ruin it will give you an age that doesn't have any meaning, okay? And so some geomorphologists in the department, Dr. Joel Pedersen and James Mock, his graduate student, they sampled some sediments up here in Mill Creek, and then they sampled some down here. So on either side of the major faults, here's the fault zone right here. And that luminescence dating revealed an age of 100,000 years on this side of the fault, and 100,000 year sediment much farther down on the landscape on this side of the fault. And remember that this valley is sinking, and it's sinking because there's a bunch of old salt underneath the Moab area, and it keeps dissolving and sinking, dissolving and sinking. But so this 100,000 year bit of sediment probably used to be up at the same elevation as this one, and it has slipped about 50 meters since 100,000 years. Okay, so that's a slip of 50 centimeters per 1,000 years, or a half a centimeter per decade. Okay, and so that's an example of applying geochronology to a geologic question that's a little bit older. Okay. Now, we're going into deep time. Hold on. here is where we are in the time scale, and here is what we think happened several times in Earth history. And so there is a hypothesis out there that is holding strong called the Snowball Earth hypothesis. And the idea is that the Earth looked like a snowball from space, and it was completely covered in kilometers of ice for millions of years, okay? Not unlike Enceladus, one of Saturn's moons, that also looks like a snowball floating out in space. But why do we think that that the Earth looked like a snowball and that the Earth was frozen over? We must have geologic evidence and hypotheses that make us think this. Let's see where we go. Okay, now, wish me luck. Hopefully there's a movie in here somewhere. There it is. So I don't know how to trim YouTube videos and embedded YouTube videos. I thought I did yesterday, but it turns out I don't. So just bear with me, because I have the minutes, the seconds written here where I want to take you to show you some pretty cool stuff. And the idea is that once Earth gets past about, snow gets about past 30 degrees north and south latitude, it'll have a runaway ice albedo effect and go all the way to the equator and become a snowball in space, okay? So right now we have ice at the poles. If that ice grew just a little bit more, if it got colder and colder and it got to 30 degrees north and south latitude, it would very quickly seal the deal and be completely covered in ice. And we think this has happened at least 3 times in deep time. Okay. Now, some people don't like this hypothesis because how would you get out of a snowball Earth? How would you get, so there's kilometers of ice all across the globe. The ocean is underneath and is completely out of communication with the atmosphere. And the hydrologic cycle has been completely shut off. And it's just really a hard state to imagine. But we really do think that this happened. So does anybody know how to get out of a snowball? Because we must have gotten out of it. Volcanoes. Why are you going like this? That's a volcano? Okay. All right, so now I'm going to go to 316. All right, check this out. I might have to unmute it. Well, maybe it doesn't matter. Anyway, volcanoes don't care whether there's ice on the planet or not, okay? And we've got an active mantle in the interior of the Earth, and so magma is still going to come up into the ocean and onto land, and it's going to eventually break through that ice. And what comes with volcanoes? What kind of gases come out when a volcano erupts? No, you. Dust. And sulfur. Anything else? Rocks flying all over the place of every size, absolutely right. And? Nice, okay. Thank you. Whew. We are moving right along here. All right. Get me out of this video. All right. Now I'm going here. I'm going to go to that. And, okay. You got to change something again? Yep. All right, but I'm where I want to be. So who here in the audience has seen a glacier? A lot of you, okay. And have you noticed, oh, Gary and Tammy have seen a glacier, woo! So you've seen it on the Googles? Yeah. Yeah, that doesn't count. It kind of counts. It's better than nothing. Okay. So glaciers, when that ice accumulates, it accumulates all sorts of rock pieces along its way, and sometimes there's landslides that come down on the top of the glacier, and it can be just a conveyor belt of sediment. And when that ice finally melts, it's like a dump truck dumping whatever's there, a dog's breakfast of sedimentary rocks. And so you can see here there's big boulders, and there's a lot of finer grained material here, and it's all mixed up. Okay, so that's what a glacier deposit looks like in the modern. That's how you know if the ice wasn't there anymore, you'd look at that and say, oh, I bet a glacier melted from here, because that really looks like what glaciers deposit, okay? Well, one of the main tenets in geology is something called, I know you told me not to say this, but it's called what? Uniformitarianism. That's why she told me not to say that. The present is the key to the past. And the way we learn about Earth's past history is by looking at modern examples, looking at modern processes and modern results. And so here's a modern process and a modern result, and that is a lithified version of glacial sediment. So that sedimentary rock, it's called a conglomerate, but it has the features in it that makes it glacial in origin. And so when we find rocks that look like this, they're actually bending down some of the softer laminations underneath of it. There's I don't know, some kind of crazy geologist for scale. This is in Namibia, and this is interpreted as a glacial deposit. Okay, fine. There's a glacial deposit, no big deal. And we know it's older. We know it's on the older side. We didn't know how old these things were. Okay, but it turns out we find these older glacial deposits and all these yellow dots and red dots on the planet. We find them on all continents except Antarctica, and they're probably there. They're just covered in ice. But so here are our glacial deposits here, but on top of the glacial deposits, we find a really, really strange rock, okay? So here's my friend Pippa. He's at that same boulder that I went to, and his hand is on what we call a geologic contact, where you have this glacial deposits below, but then a very, very different kind of rock above it. And it's a carbonate rock. And the glacial deposits obviously indicate cold conditions, but these rocks above it actually represent very warm conditions. Something like where we'd all like to be right now. Okay, that's the Great Barrier Reef, but these big, nice, warm, shallow seas on some kind of a continental shelf, like the Bahamas, Costa Rica. Let's go. So that should bother you. And closer up here, let's look at these rocks. And there's some in the after talk activities. You can go and see some of these rocks, but you can also hike to Fairy Peak and on Antelope Island, and you'll walk right by them, and you'll see this very thing, and you'll say, oh my gosh, those are Snowball Earth rocks. So these are rocks from Antelope Island and Utah, and these are rocks with those same features in Mongolia. And both of these rocks, if you cut them from the side, they have these funny little tube structures in them. So we call this tube stone, and it's the only example of tube stone in the rock record. So it's something very different, okay? And we find these above the glacial deposits on all continents. All right. So there's Pippa again. There's our glacial rocks. There's our tropical rocks. So we're going from an environment like this, but more extreme than that, if it's a Snowball Earth, to an environment like this in a blip of time, okay? Which is quite a paradox. But the deal is that we have these deposits, the glacial ones and the tropical ones, on all of these different continents, indicating cold, rapidly going to warm. So we call this a potential mega ice house, rapidly turning into a mega greenhouse, okay? But we didn't have a sense for the time it took for a Snowball Earth, and we didn't know even if all of these deposits were the same, because we've had glaciations all throughout Earth history. Why do all of these have to be the same age? But if they are the same age, it says that we had ice at the equator and in polar regions and everything in between, okay? Snowball Earth. All right, so how do we get at dating some of these older rocks? And the main way we date deep time rocks is with this beautiful, beautiful, beautiful mineral called a zircon. Zircon to the rescue. It has been truly transformational in deep time science. And this zircon is on the larger side, but it's still smaller than the diameter of the cross-section of an angel hair postal noodle. That was the best analogy I could come up with. Maybe not too good, but it looks pretty delicious. Okay, so what? So zircons, periodic chart, right? You've seen this before? Okay, nope. Okay, you're seeing it right now. So the element zirconium, the element silicon, and then oxygen join together to make this incredibly robust, gorgeous mineral. And also, an element that's found in zircon is uranium. Okay, when it originally crystallizes, like out of a melt, it has a lot of uranium in it. And what property does uranium have? Radioactive. Do you know what it decays to? Does anybody know what uranium decays to? Lead. Lead. Uranium decays to lead. Okay, but there's no lead when the crystal first crystallizes. Okay, so number one, zircons are amazing minerals. Number two, they are found in a lot of different rock types, sedimentary, igneous, and metamorphic rocks. And they're very, very durable. And so they're not sensitive to heat and pressure. And so these things can stay around for billions of years and not lose their original chemical signature. Okay? So when the zircons crystallize, there's only uranium inside of that silica oxygen zircon structure. But the uranium is radioactive, and eventually, through time, this uranium starts decaying to lead. And all we need really is the ratio of uranium to lead and understand how fast these different elements decay, and we can get the age on rock, okay? And so we call these geoclocks for older rocks. And very importantly, zircons are ubiquitous or very, very present in volcanic ash, okay? So in a volcanic eruption, when all that ash is flying out, there's a bunch of think of those little tiny zircons just blanketing the landscape. Isn't that a beautiful thought? It's kind of calming. Okay, so here's just more beautiful zircons. And so this is an example of volcanic ash and how it blankets the landscape. And then down here, if you look closely, do you see there's cobbles and pebbles and stuff? This is actually one of those glacial deposits that I was talking about. And Tony Prave in the Congo of Africa found a beautiful ash deposit right there in the Congo, and he marked where he was, and he sampled that ash, and he ground it up, and he extracted the zircons out of it. And some of the zircons aren't whole, some of them are broken, and one of the zircons looked like this. And then what he did was he put that zircon, that yellow thing, into a gas chamber, and then he pulsed it with a laser beam. And what that does is actually ablates the zircon, so it goes directly from a solid to a gas, goes through the plasma, and then is collected based on the atomic mass of each individual element. And so all the uranium goes in one little cup, and all the lead goes into another cup. So we have everything we need to calculate the ratios of uranium and lead, and to also get the age of the zircon, okay? And if you really want to know, this is a sketch of a laser ablation inductively coupled mass spectrometer. And that's what you need to be able to do this this study. And a lot of these figures are actually from the Lasercron lab down at University of Arizona. Okay, so the results, Tony's ash that he was down in the glacial deposits came in at about 640 million years. I'm only showing you these because these are actually what are shown in scientific papers to report the ages. And you want to see nice straight lines, and there's different uranium-lead ratios plotted against one another. And there's ashes in some of the weird cap tropical rocks, and those have come in on 5 different continents, ashes that are all coming in at 635 million years. Okay, so we're finding that these glacial deposits are the same age, and the weird capping rocks are the same age. Okay, and so for this particular glaciation I'm talking about, you would have sort of normal polar ice. Something happened to make the planet colder. It got down to 30 degrees north and south latitude, went all the way to the equator, and we know there was ice at the equator at 640. But remember that the crazy cap tropical rock is indicative of warm, shallow waters, so the ice had to be gone by then. And so by 635, there was a greenhouse, a deglaciation, okay? And so that's an example of how we're trying to get at the Snowball Earth, and I left out a lot of details and pretty much lied to you. No, not really. But if you have more questions about how this all works, please ask me after the talk. And one last little teeny tiny, I have to show you another zircon. Here is Australia. Here are the Jack Hills of Australia. And in a meta-sedimentary rock in the Jack Hills of Australia, we have found a zircon. John Valley's group out of the University of Wisconsin found a zircon that is 4.4 billion years old. And prior to this time, the oldest Earth material on the planet was the Acasta gneiss, which is about 4 billion years old. Okay? But our early Earth record is very, is either non-existent or there's just a few geologic features, and this is one of them. So this tells us that the Earth can be no younger than 4.4 billion. And it also tells us that plate tectonics were already operating on the planet in some way by this time, because you need continental crust or pretty light frothy crust to make zircons, okay? And you need water, which also tells us there was probably already water on the planet at 4.4, okay? So, back to that arm. You're okay though, you can stay there. So thinking about some more deep time events, and this is my final slide, let's look at that arm again and remember that we are way down there. And Earth began here at 4.6, and we had, we've learned that with geochronology, we've learned that the moon evolved about 30 million years after the Earth was born. So they're not the same age. I had never really thought about how old the moon is, but the moon is only 30 million years younger than the Earth, and is probably a piece of the Earth in part. There's our oldest zircon, and our earliest evolution evidence of biological activity is at about 3.7, 3.8 billion years ago. And that weird-looking thing is actually a supercontinent. We know that all the continents came together. What's the name of the supercontinent? Thank you. That's the last supercontinent, my friends. That's way up there. That's way up there. But so there was a supercontinent around 3 billion. There was a Snowball Earth, an older Snowball Earth. And then about 2.3 billion years ago, we had the great oxidation event where enough photosynthesizing occurred to flip our atmosphere to an oxygenated atmosphere. Hello? So before that time, the Earth did not have an oxygenated atmosphere. It was uninhabitable by organisms that need oxygen to live. So that's an extremely important turning point in Earth history. we started to have more complex life show up about 2 billion, another supercontinent or two, even more complex, maybe even multicellular eukaryotic organisms at this time that actually had advanced food web capacities and did things like ate each other and stuff like that. It was pretty cool. Our Snowball Earth that I just talked about, there's when skeletons show up in the rock record. There's our Pangea that everybody just talked about. And remember that we are at the very, very, very tippy edge where that pink line is. Okay? And so that might give you a slightly different perspective on things. And that's all I've got. Thank you. Aw, someone didn't like the talk.
So we've got a few minutes for questions.
Would anybody like to ask a question?
And please, if you have to leave now, leave quietly so people can hear questions.
Who has a question? Oh.
What's your question?
How did living things survive through all of the Snowball Earths and changes in the Earth's atmosphere and crust changing?
First of all, give me a high five. That's a totally brilliant question. Just like people didn't like the Snowball Earth hypothesis because they couldn't think of a way to get out of it, they don't like that hypothesis because life would never be able to withstand such extreme conditions. But I know. But evolution is a one-way street, and there are organisms that you can find in the fossil record below the glaciations, so stratigraphically below or older, and then above the glaciations. And so there are thermophiles, or in this case, cryophiles, organisms like different kinds of bacteria and algae that can withstand really extreme conditions. There could even be something on that moon and Saturn. So, but life made it through the snowball. And some people wonder if there was a little bit of open water here and there. They're referred to as warm puddles. And in equatorial regions, that would act as refugia for certain organisms. But that's an excellent question.
Thank you.
Yes. Hi.
Quick one. Have we seen examples in human history of volcanoes raising the temperature of the Earth?
Oh, I think so. I think one example is Pinatubo. When Pinatubo erupted over a decade ago, yeah, the ash spread all the way across. It was basically like a very temporary nuclear winter. And it raised the temperature on the planet around 1.5 degrees. Oh, awesome. Yes? How hot is the Earth's core? Is Tony here? Jim, how hot is the Earth's core? 6,000 degrees Celsius? 6,300 Kelvin. And by the way, if you've seen the movie The Core, you cannot go down there and walk around. So don't try that. Are there other questions? Quincy. This is going to be bad.
So you said that the volcanoes destroyed most of the Snowball Earth, but did the Earth have any effect on that? Or no, the sun, did that have any effect?
Oh my gosh, another brilliant question. So to fit all this in today, I did leave out a lot of very important details like the faint young sun. Our sun is much hotter today than it was during the last Snowball Earth. The solar luminosity was at about 90%. of today's, and so the Earth was overall cooler with respect to the sun's heat, and was definitely one of many players that caused Snowball Earth. Excellent question. Yeah. Other questions? Somebody has a question over there? Oh, here, I'll get one on the way.
How hot does the Earth's core have to be for it to get out of the Earth?
To create volcanoes.
Yeah.
Why do volcanoes happen?
So how can it get hot enough for it to get out? How hot does it get?
I'm not going to kid you here. I can't answer that question. Is there any geologists in the audience that can help me out? Jim. Jim says no. We'll get back to you on that. Okay? Does someone have an easy question?
How come it took so long for all the volcanoes to erupt on Snowball Earth and to end it?
Oh, that's a very, very good question. Yeah, there was probably volcanic activity throughout, but that last chart I showed you, that snowball glaciations actually lasted for millions of years. And what the climate modelers have figured out is the CO2 that comes out with each individual volcanic eruption has to accumulate in the atmosphere to get to a point to cause a shift in temperature and cause the ice to melt. Okay, and that's one of the ways they calculate, before we had ages on these rocks, how we calculated how long one of these glaciations had to last, because it had to be long enough for the CO2 to build up in the atmosphere. Another excellent question. And you?
Do you know what caused the Snowball Earth?
What caused the Snowball Earth? Well, that's an excellent question. One thing that we think is definitely a cause is that from the evidence we have so far, the majority of continents were in equatorial or near equatorial regions during that time, okay? And continents have a higher reflectivity than oceans, and they're like mirrors. So when the sun shines down on the equator, if it hits these mirrors, that's going to reflect that heat back into the back out of the Earth's atmosphere. And so if you have mirrors on the equator, that's one way that you can start getting global cooling. At the same time, we call upon the biota at the time who were photosynthesizing, putting lots of oxygen into the atmosphere at the expense of carbon. A lot of carbon was getting pulled out of the atmosphere as basically little carcasses of microbes. And so that also started cooling the planet by lowering the amount of CO2 in the atmosphere. And thirdly, if the continents were all in equatorial regions, they would be subject to tropical weathering, extreme weathering, and extreme weathering of silica crust demands CO2 also, so that was pulling down CO2. So, and we had a faint young sun. So it's definitely a combination of different things. But really good question. Question over here? Yes.
What caused the holes in the tube stones?
What caused the holes in the tube stones? What an awesome question. Do you want to come work with me? Because nobody else cares. Holes in the tube stones, that's super cool. Actually what they are, those are microbial, those are built by microbes, and what they really are really long, skinny microbial buildups, and the tubes are the areas in between the buildups, and they make little holes. So those are actually fill in with sediment as the microbes grow up towards the light. But that was a mystery for a while, and people thought they were methane gas escape structures and all sorts of crazy ideas, and it turns out they're just basically ancient reefs, really. Yes?
Why did the snow, if the Earth was so hot in the middle, why was the Snowball Earth so hot, cold on the outside?
Oh boy. Well, the Earth was still hot down there. The Earth that deep down does not care about some ice that's at the surface. And so the expression of the hot interior of the Earth is the volcanism that continued to go on despite whether the ice was there or not. Okay? I hope that helps.
So we probably need to maybe take one more question and then go informal, and you can come down and ask Carol more.
There's four hands. Can I do four?
I don't know. Do you want to sit still for four more, or do you want to take a break, people leave, and the rest of you stay for four more? You
Yeah,
can
I
pick.
mean, anybody who would like to leave could leave, and other people could ask questions.
That
Okay,
works.
because these young ladies are just going crazy over here. I might have, what's your question?
Okay, we're wondering what would be needed to happen again for the Snowball Earth to occur.
Oh my gosh, the question is, what would need to happen to have another Snowball Earth occur in the future? I got to sit down for this one. What I can tell you is that it's not impossible, but what I can also tell you is that it would have to be a different set of conditions than those particular ones that happen to coincide at the same time to cause the global cooling before. But I'd say it's not impossible. Maybe when the sun's starting to dim again, when the sun is starting to burn out, and if all our continents are in the equator, Pangea Ultima, in 150 million years, we're supposed to have all the continents in the equator again. Looks like a donut, actually. So it is possible, but an excellent question. All right. Who else? Yes, young lady.
How much
Oh,
pressure?
you got cut off.
How much pressure in a volcano does it need to explode?
I have no idea. Where are you guys getting these questions? There, young lady.
How long would you say each of the Snowball Earths lasted?
Oh, excellent question. So one lasted for 60 million years, and one lasted for 5 million years. And those are spaced apart by about 10 million years. So they were pretty close in time, between 720 and 635 million years ago. And then there's one way back in around 2.9 billion, and that one, there's fewer rocks available from that time, so we know less about the duration of that one. But they look similar to the rocks that we have, that we talked about today. Don't ask me about volcanoes.
Why?
Go ahead.
How do the volcanoes rise up on planet Earth when it was covered with ice?
Because volcanoes don't care about ice. Right? They're happening anyway because those are from internal processes and heat from within, and gas is trying to escape. And so if there's ice on the planet, the volcano doesn't care. It still needs to do its thing.
I think some geology is entering the room. We may be in a new era.
Oh my gosh. Oh. Wait, I thought those went extinct. Oh, you're dying to ask a question. Yes.
Okay, so do you believe that the moon is actually an alien spaceship looking over the planet Earth?
Absolutely.
So for those of you who are still here, let's thank Carol.